Time is 9:30, so let's begin class. So for today, you needed to finish off the notes, finish off the videos. I'm sorry. Let me start again. So today you need to examine the end of subsection 3 and then do subsections 4 and 5 of section 2. Watch the videos, take a look at the notes. So a real brief review then of this corresponding materials as follows. So at the end of subsection 3, we started looking at the autocorrelation function. And just like in your very first stat course when you learned about irregular old correlation, we look at a correlation instead of a covariance because the correlation is bounded between -1 and 1. And so the problem with the covariance is not. And so this gives us information about the strength of the dependence, and this can carry forward to essentially to any situation because it's always between -1 and 1. And so with respect to the autocorrelation function, this is what it looks like. We have the autocorrelation at time s and time t. So for x of s, x of t. In the numerator, we have the autocovariance function at time s, time t. And then in the denominator, we divide by the square root of the variance at time s times the square root of the variance at time t. Now, we will look at the derivation of many of these autocorrelation functions for a variety of different time series models throughout this particular course. The key thing is that, once you have the autocovariance function, then it's fairly easy to use to get the autocorrelation function. So the tough part is the derivation of the autocovariance. And then we started looking at what different autocorrelations mean then in the context of a plot of our data over time. So, if we have a smooth plot, meaning that points tend to maybe keep on going up and then maybe they start going down like this, then we're going to have a positive correlation. If instead, though, we have a point that's here and then if we jump up to the next point and then we jump down and then we jump up, then we have a negative autocorrelation. Make sure you understand why one would be positive, why one of them would be negative. And so this helps relate then to these plots that we have over time. And again, what we're trying to do is understand this dependence that we have over time so that we can come up with a model for what has been happening in the past and the present so that we can then forecast the future. So in subsections 4, then we talked about a very important concept in time series analysis called stationarity. The basic reason why we need to have a stationarity is that we want to project into the future. Or I have a different idea to explain it. Imagine we go back to your very first stat course. We talked about a plot like this similarly. And last time, I think, we have, that should be a straight line there. It didn't come up to be a straight line, but it was meant to be a straight line. Imagine a situation where you have an X, you have a Y, and you do a scatter plot of points, and you put a straight line through the middle of those points. Now, if I wanted to predict at a particular X that was like right here, in terms of, if I project up, if you were to project then that straight line over, our projected or our estimated Y would be where my yellow highlighting mark is. But that's extending beyond the range of our data. It's extrapolating. And in regression analysis, you're told not to do that. But if the same trends hold true that you experience between, let's say, this X and this X, this would be a reasonable estimate. And for us, you can kind of say that stationarity kind of gives us that in the context of a time series model. we observe information from, let's say, time point 1 through time point 100. And if I want to project what's going to happen at time point 105, well, that's going beyond the range of my observed values. But as long as the same trends hold true, well, I could have some accuracy then with that projection. It makes sense to do that. And that's essentially what stationarity allows us to do, is that if our data maintains the same mean structure, you could say, meaning the mean is going to be the same over time, if it's going to have the same dependent structure over time, well, then it seems reasonable then that if I were to project out to a future time point, as long as that still holds true, I'm going to have some accuracy then with my prediction. And so that's some of the main concepts behind, or main reasons, why stationarity is a very important thing. And so in time series analysis, we tend to stick with or focus on this weekly stationarity for a number of reasons. One of them is that it's just easier to look at. Weekly means the mean is constant over time, and also the autocovariance for lag H differences does not change over time. So the dependent structure remains the same. It only matters what the difference is between, let's say, time S and time T. And so once we have that, then our autocovariance function actually nicely simplifies. Now I only have to worry about this lag H difference between time S and time T. And so now my numerator is just simply expressed as gamma of H. My denominator, notice how up here I had two autocovariances, one at time S, one at time T. I square root of them. Notice there's a lag zero difference between time S and time S, time T and time T. And so what ends up happening is then this all simplifies down to simply just gamma of zero. So lag zero difference. We can actually check for stationarity, weekly stationarity, through some derivations. Not too difficult, just check what the mean function is. Does it change over time? Check what the autocovariance is as well. And then once we have stationarity, then we can go to this really big result. And perhaps I need to emphasize that more in my notes. The importance of this result is maybe a little bit difficult to see right now, but starting, I think, with our next set of notes, you'll start seeing it pop up again, the end result. And that basically is that if I have this linear process, so notice, x of t could be, let's say, the S&P 500 index value over time, or x of t could be the number of earthquakes over time. If I can write my x of t like this, where I have some mean value, notice how it remains constant over time, there's no subscript t, and I can write it as an infinite sum of some white noise terms multiplied by some constants, these psi's. With stationarity then, I can get my autocovariance function. There's a simple, I wouldn't say simple, but there was a derivation in notes that showed that. So I can get this autocovariance function. And right now you might be thinking, okay, well, this works nice if you have these W's. You could write, stuff is just in terms of white noise. But what we're going to find out is that we can very often rewrite anything that's not white noise as a function of white noise. And so if we can do that, then I have a way to derive what the autocovariance function is. Then I have a way to get the autocorrelation function also. So we've talked about briefly, what a autoregressive model looks like. We saw something like this. I think I'm using the same numerical values. If not, I don't think it's a big deal. So an autoregressive model could look something like this. X of t is equal to 0.7 times x at time t minus 1 plus some white noise. I can actually rewrite this part here in terms of only white noise. And you'll start seeing that in the next set of notes. And that's going to be a very useful tool for us. Then we started looking at, well, what does stationarity mean in terms of if I were to observe some data? What would it look like in terms of if I were to plot over time? So if I had some kind of plot such as this, let's say, we'll just do this. And not a very interesting time series. Notice it just is going up like that. Well, this is a case where you would expect, even though we're only observing a finite number of time points, you would expect this not to be stationary, because probably like the mean is changing over time. In the next set of notes, subsection 6, you'll look at how we could do a little transformation of our, let's say, x of t, so that it can actually be thought of as stationary. Okay. Then in subsection 5, now we start looking more formally at data and calculating statistics with this observed data. And we looked at the sample autocovariance function, the sample autocorrelation function. So, where we have a parameter, we put a hat on it to mean it's an estimate. Some time was talked about how we could do inference for an autocorrelation. Very often, we are interested in the following hypothesis test, that rho of h is equal to 0 versus rho of h does not equal 0 for some particular h. We want to do this hypothesis test. And the big picture reason why? Well, if there is no autocorrelation, then that means the past observations are not going to be probably helpful to predict future observations, because there's no dependence. But if this hypothesis test ends up rejecting HO, then that tells us, okay, now there is some dependence here. How can I take advantage of this dependence to forecast eventually the future? Okay. And the way that the hypothesis test was done was probably a way that very often students do not see before coming into this class. I didn't necessarily define a test statistic and then calculate a corresponding p-value. I didn't define that. Instead, what I did was I basically looked at a range where I would expect observed values of the test statistic to fall within. And if it fell outside this range, then I reject HO. So it was a little bit of a different way of looking at things. I don't know, sometimes when I teach SAT 801, I show that as well, just like with a hypothesis test for a regular old population mean. But if there were questions about it, please let me know. And then lastly, to help simplify the calculations, we have the ACF function in R. We'll be actually looking at that a little bit more closely here today. And this was going to calculate your estimated autocovariance or your sample autocovariance, your sample autocorrelation. It's going to help you perform this hypothesis test. It's going to perform a nice little plot of these ACFs. Okay. Again, I talked a lot here. Are there any questions about the corresponding material here for today? Okay. So let's continue talking about project number 1. Then I'm going to make a small note about notation that I use. And then we're going to spend then pretty much the rest of the day talking about one particular example dealing with COVID. So again, project number 1 is due on February 15th at 8 p.m. Let's go ahead and take a look at that. Oops, there we go. So this very first problem dealt with these earthquakes. And we have number of earthquakes per year. And I'm interested in, is there some kind of dependence over time? And the reason being, and then eventually we will get to forecasting what the next year's number of earthquakes would be. And some of the motivation behind this for me, again, was, very often, like when it's hurricane season at the very beginning, you'll see some kind of forecast made that there will be 12 major hurricanes in the northern Atlantic Ocean this year. And, well, they had to probably use some kind of time series models for that. And to be honest, I don't know exactly their methodology, but I thought it would be interesting to apply some kind of forecasting then method to, let's say, the number of earthquakes. And you would expect that, or at least I would expect that, there would be dependence over time. You could think that, let's say, if you have a very active year in terms of earthquakes, maybe that might lead to the next year also being very active because there's some instability in the Earth's crust, you could say. I'm not a geologist, I'm not an expert in it, but this was something over winter break when I was preparing for the course. I thought, that would be interesting to take a look at. Okay, so we've already talked about, well, let's read in the data, let's plot the data over time. Now part C now starts applying some of this stuff that was the material for today. Plot the estimated ACF for the first 20 laps. So what function are you going to use? ACF function. That's the easiest way to do it. I suppose if you really wanted to calculate all this stuff, program in the function, the actual estimate autocorrelation function, program in R, you could do it that way, but that would not be the most useful way to spend your time. So, of course, with this function, then, and I just kind of explained this, you're going to get this plot. This plot's going to give you some tools then to perform a hypothesis test of, is rho of H equal to 0 or not for H equal 1, 2, all the way up to 20. So, based upon what you see on this plot, are there any true autocorrelations that are significantly different from 0? Make sure you tell me why. This is just a way for me to verify that you know how to properly look at the plot. It should not be difficult. Then, see if you can relate trends that you saw for the plot over time of this data related to what you're seeing here for these autocorrelations. So if these estimated autocorrelations, maybe the first estimated autocorrelation is positive. Relate that to what you're seeing for the plot of the data over time. If instead it's negative, that first estimated autocorrelation, then you should be able to relate it to that plot over time. And the purpose here is for you to be able to match what this dependence means in terms of these summary measures to what is actually for a plot of data over time. That's the purpose. Then part D. So the way that I taught about how to make the judgment, and this is a standard way to do it, make the judgment about the hypothesis test is that you look at a interval, 0 plus or minus the 1 minus alpha divided by 2 quantile from a standard normal divided by n. You look at that interval to make a judgment about, is the true autocorrelation equal to 0 or not for your hypothesis test? Now what I want you to do is tell me, if you were to actually write out a test statistic, what would it look like? Then show me, how would you actually, with the calculated value of the test statistic, how would you actually calculate a p-value? So, what do we have here? We have information about rho hat of H, we have information about rho of H, and we have information about the estimated it's square root of the estimated variance of rho hat of H. Okay, that was all given to you in the notes. And what I could do is make two other little small marks on my document here, and I would get what the test statistic is. This is going a little bit beyond than what's in the notes, but that's okay. It's meant for you to connect what you've learned in other courses about hypothesis testing to now this situation. So I do want to actually formally see in terms of symbols what that test statistic would be. I want to see what the probability calculation for the p-value would be in symbols, and then actually implement it with the actual numerical values that we have for lag 1. Any questions about that? Now, part E here relies on some stuff regarding the stationarity section when we are looking at the plots of data over time, but it also relies on something that's in subsection 6 as well. In the end, what you'll learn about in subsection 6 is that you can use an ACF plot to help you make judgments about stationarity as well. So that's problem 1. So problem number 2, again, deals with the number of visits over time for my Shiny app. And with this, we talked about reading in the data, doing some plots over time, and now you're going to do some of the stuff that we just saw in number 1. You're going to plot the estimated ACF. But we're going to go up to 50 lags. Why do you think I want you to look at a higher number of lags rather than the default of 20? You're on the right track. I wouldn't say monthly. So this data is observed daily. And sorry if you needed a reminder about that. It's observed daily. And you might expect what happens on a Monday for 1 week to be similar to what happens on a Monday of another week. What's the lag difference? 7. So if I go up to lag 50, then this will allow me to look at what's happening, let's say, lag 1 to lag 8. I'm sorry, let me restate that. I'll just say it this way instead. It will allow me to look at 7, 14, 21, 28. Maybe what happens, let's say, 2 Mondays from now is related to this Monday. Maybe what will happen 3 Mondays from now has a dependence with the current Monday. And so by looking at a larger number of lags, this allows me to see this dependence that could come about simply due to I'm observing data daily, and we would expect in a work environment that, for example, Saturdays and Sundays, maybe there's not going to be as much, let's say, activity, not as many people in the lab in comparison to, let's say, on a Monday or Friday and so on. And so if there is some kind of dependence like that, I'll be able to hopefully see it. Part F relies on subsection 6. Part G then addresses weak stationarity again. Now, since we're working with observed data for both 1 and 2, there are no derivations here. What we're going to be doing is examining like these plots of the data over time that you've saw in subsection 4. But then also in subsection 6, we'll look at how we can make judgments about stationarity with respect to the ACF. Okay, so that's part G. Number 3 is also a subsection 6 problem. It's just a little bit of math involved with it, and we'll talk a little bit more about that next time. Excuse me. Then number 4, we've talked about part A and B, where you're deriving the mean function, you're deriving the autocovariance function. Now you need to make a judgment about weakly stationary. Very similar to what you saw in the notes for subsection 5. Okay, so that's the project. Again, if you haven't started the project yet, or I shouldn't say that, but if you are looking for a time to get together with your group members for the project, come to this Thursday help class that we have. You can work on it in here. You can bring a laptop to work on it. Obviously, you have computers here you can work on, and I'll be available to answer any questions that you may have. As a reminder, make sure to always include all R code and output in your projects. In case I didn't say this before, one of the reasons is that I will often execute your R code and output to verify it worked. Or if I see something kind of odd in your code that I wasn't expecting, I shouldn't say odd, but something I wasn't expecting, that's often something that tells me, okay, I want to double check that this code does actually run correctly and stuff like that. Of course, if you end up getting a problem incorrect, by me seeing your R code and output, this will help me diagnose what was the issue. So that's why I do require that. Also, please make sure to use the proper formatting for the R code and output. The code and output should look like what's in my notes. To help you with that, I put together this R10 style in Word that you can apply to your R code and output. And again, make sure you use the correct notation. So gamma is the actual Greek letter gamma, not G-A-M-M-A, for example. Okay. So a very small note about these quizzes. So on these quizzes, you will notice, and perhaps it's not a big deal, but I'm going to bring it up anyway. There's 2 things. This is actually from quiz number 4 coming up. Notice how the letters there are italicized. In my notes, I don't italicize. They're meant to be the exact same thing. Okay, the italicization doesn't mean anything. It's a little bit easier in Canvas, and Canvas is the equation editor. I don't think it's really the best, and it's just easier for me to use the default, which would be to italicize. So that's why I do that. And then second here, you will often see problems that look like this. So this is just continuation of the same problem, where notice how I write out, this is actually a particular model that we're going to look at. The underscore here is a way to represent subscripts. The caret sign that you're probably all familiar with is a way to represent superscripts. And so you will often see me use kind of a text-based way to write out something in Canvas when I have multiple choice answers listed like this. The reason why I did this is that, about 4 years ago, I started using these Canvas quizzes a lot in my courses, not just this particular course. And at that time, I don't think there was a way for me to use an equation editor in my answers for a multiple choice quiz question. I couldn't find it. As I was preparing for class today, I noticed that, there is one now. And somehow I've missed that. So at least for the most, I guess, the quizzes coming up, with quiz number 4, at the very least, you're going to see me use some of this odd notation. I don't think that there should be confusion with it, but if you're not sure what something means, let me know. And hopefully I can start making some corrections with or revisions for future quizzes. Okay, enough about that. So for the rest of the time today, we're going to talk about an example for time series analysis with COVID. So, the statistics has played a very large role during the pandemic. It helped us understand the accuracy of tests to detect the virus, SARS-CoV-2. It helped us understand how effective vaccines were. It helped us improve the testing efficiency, meaning that we could do more tests. And it helped us monitor stuff like infection rates over time or other things that were important regarding the pandemic over time. The reason why that was important is because we wanted to understand, what were trends that were occurring. So, for example, if we started seeing an uptick of infections over time, then that might lead to, let's say, public health officials saying, okay, now we're going to have a lockdown and you're not going to be able to live your normal life. You're not going to be able to interact with other people so that we could prevent the virus from spreading. And so some very basic methods that we would talk about, or very basic time series analysis methods, were used. I've always been interested to see if more sophisticated methods were used. At least I didn't see them too much, but perhaps I just didn't see them. And so, what we're going to do is to take a look at, for the county that Lincoln's in, Lancaster County, we're going to take a look at some data that has been collected during this pandemic and investigate it with some of our time series analysis methods this semester. And if you do a simple Google search or any other search on the internet for COVID, Lancaster County, Nebraska, you need Nebraska, otherwise you get Lancaster County, Pennsylvania. You'll come eventually to a webpage like this for Lancaster County, city of Lincoln. And if you click here, Lincoln Lancaster County COVID-19 dashboard, many governments, entities had dashboards like this during the pandemic. Lancaster County still has one. And this gives you some information about what's happening with the pandemic. And so what we see here, what it defaults to, is that we see a plot here of the number of confirmed cases over time. And it looks like something like what we would see, what you've seen in this class for other data examples. And so you might be wondering, okay, well, what kind of dependence do we have over time? And can this dependence be used to understand what's going to happen in the future? Okay. Now, let's see here. So when I last taught this course 2 years ago, this was obviously really at one of the big points of the pandemic. It was a spring 2022 class, and this was probably one of the worst time periods in terms of the number of infections that were out there. And I'm going to talk just a little bit about 2 years ago, and then I'm going to talk about a new data set that I'm going to be using for our class here. And so if you're interested in taking a look at this data that I used 2 years ago, this is the data here. And what this simply gave us was the number of confirmed positive cases for COVID, or more specifically, I should say, the number of cases where there is SARS-CoV-2 was detected. SARS-CoV-2 leads to COVID-19, and the test actually looks for the virus. And I know that might be a little bit tougher to see there because of the contrast in the colors. Let me see if I can even make it a little bit bigger. But at the very beginning here, we're in 2020, March. Here's 2021 if you follow where my mouse is. And then eventually we get up to 2022. So for example, in about January, right about when we're starting the semester, we had about 5,000 cases reported in one week in Lancaster County. And so we were really not in a good situation at that time. But what we see here is waves, you could say, of the virus or of the infections over time. So you would think that there's some dependence. Like, if I am, let's say, high here, well, then I expect to be high here as well. But there are some problems with this data, at least the way that was reported to the public. One small thing was that I found to be disappointing, I'll say, is that the most recent counts were changing. One day you will look at the counts, you might have 1,000 confirmed cases. The next day you might have 1,100, even though this was all in the past. And also some of the counts were only rounded, and so I couldn't get the exact counts. And so, I thought about what would be really interesting in this class is, well, how about we extend this plot now to 2024? Because this data is still being collected. But there are some problems with using the data that they provide beyond what I just mentioned there. What do you think would some problems be? Exactly. So back about January 2022, in-home tests were not that big yet. So these are probably more accurate count. These are fairly accurate in terms of cases. But nowadays, we have in-home tests. And, you're encouraged to report if you're positive or not after taking a test. But probably a lot of people don't do that. What's another problem? People just don't care. Okay? Oh, yeah, I'm feeling, feel a little sick here. I'm not even going to get tested. So we're probably missing some cases that way. And so, this is a big picture thing about, statistical methods are only as good as your data. And if you can't get good data, you can't do statistics on it. So because of that, I thought, okay, now I can't use the same data and extend this example now like I had wanted to. And so, but what can we do? You probably have heard about this. Public health officials have now turned over the last couple of years to using wastewater, monitoring the amount of virus in wastewater to make a judgment about how big is the problem, how big is the in terms of the number of people who are sick and stuff. While I guess that's a messy business to do that, it can still be a very good proxy for what we're really interested in is who's sick and who's not, or how many people are sick. How bad is it going around? Is the virus spreading a lot in the community? And so we're going to take a look at this particular data set, covidwastewater.csv. It's available on my course website in the section materials webpage. And what it's going to basically provide is the data that would that produces this plot that's available on the Lancaster County dashboard. Just in case you ever wanted to go to it, the way that you can get to it is if you click on testing. Down below, if you see where my mouse is, you see wastewater. And this is what they actually provide. If I were to, let's say, mouse over one of these dots that you see on the plot, that tells me, I know that's very small, it tells me the weekly concentration, I guess, per liter of the virus in wastewater. So it tells me there's I'm not an expert on this aspect, there's 1.7 million virus copies, essentially, in a liter. I don't know, I guess from a non-expert on the wastewater, that seems like a lot, but this is what it's telling me, or at least that's how I'm interpreting it. And so again, we see this data over time. It looks like there's some dependence that occurs, and we want to be able to explain it using methods in our class. Now, is this really a good thing to do? Well, take a look at here what's happening in January 2022. Notice how we have this big spike in terms of the wastewater monitoring and how much of the virus was in the wastewater. Compare that to what occurred in January 2022 in terms of the number of confirmed cases. That's why we can use wastewater as a way to judge the status of the of cases. Now, what I did last month was that basically let me actually come over here. I went to this dashboard and I moused over every single point. I recorded the actual date that gives me basically a weekly date. I moused over all this here and I typed it into Excel and I got the data that way. Now, perhaps there would have been a way to do this more automated. I did not see one. If anybody sees a way to do that, let me know, because there's lots of data that's available on this website that I would like to have access to, but I don't want to always have to do what I did for our class here. Okay. So what we're going to do is take a look at this program that I've used to basically apply the methods that we've seen so far in this class to this data. This program will be made available to you sometime later today. It's not on my website yet. Let's see here. Now, throughout this, you're going to see some more of the finer points of using R. And I do that because sometimes students will miss this. They don't get this in a class. And what we talk about here in terms of the finer points of R can be very useful outside of this class for other problems. Okay, so here's my program. So obviously the very first thing that I want to do, hold on here. There it is. So this is what the data looks like in Excel. Make this a little bit bigger. So for the very first date that's available to me was June 26, 2021. It gives me a value of 68,100. Then in 1 week they did another measurement and they got to 66,000. Just a little bit of a side note. Well, where do they take these measurements? And so here's a map of the actual, I guess you could say, the sewer system of Lincoln, at least the larger pipes that are out there. I know that's a little bit small, so I'll blow it up. But So last fall, the Lincoln, I guess, oh, this isn't the right name. I'll say the Lincoln Sewer people, sorry, had an open house at their facility, which is located at about, I would say, just north of 20th and Holdridge. So if I zoom in here, so for example, if you see where my mouse is, here's where East Campus is. They're located right about here. And I would assume that that's probably where they actually collected their data. There's another waste treatment plant up in the northeast part of town. They might have collected it up there as well. But if you're driving around, I guess a little bit northern Lincoln, maybe if you're on 27th Street, if you ever see these big things out in the distance, this is where the Lincoln's sewer system, main sewer facility is actually located. Okay. And so anyway, so they had an open house out there last fall, and I took my family out there and we explored, and it was kind of interesting to see how they treat stuff. So anyway, so I have my data. I need to read my data. So simply let's use read.csv to read the data in. I'm going to put in an object called set1 for the lack of a better name. And then I'm going to look at the head and the tail of the data set. And just to verify that I did read it in correctly, and indeed I did, there's that 68,100 that we had saw previously. Now, when I originally read in the data, the first time that I did this, I noticed on my tail of my data set, I did have, for some reason, some empty rows. And that just shows you that this is important to do that. You know, it was saying that I guess I had another date there, and I had no values for concentration. And so I had to go back to my original data set to figure out what was wrong. I typed in something wrong, and then I fixed it. And so that's why this is important to still look at the data in this format. Now, if you notice that I have a variable called concentration leader, that was essentially what was on the y-axis of those plots, or that plot that we saw. And so what I'm going to do is just simply take concentration leader out of set1 and put an object x, just because it's a little bit easier to work with. And this is what I get. Do note that the very last two values here was 1.7 million. That corresponds to these two high points here. And you can see that indeed they are high in terms of the concentration of the virus. Notice that the points are not exactly the same height, but the data that's reported to me only does not go beyond 1.7 million. So that's why I left it as 1.7 million, even though it looks like there is a difference there. Okay, so now I need to do a plot of the data. So, you know, this corresponds to what you see, for example, for a problem like 1A, or I'm sorry, 1B, or 2B in the project. So I'm going to open up a new graphics window. The reason why I like to do this is because I have more control over font sizes. I have control of the width of the window. And so I'm just going to open up a nice little new graphics window. There we go. And then I'm going to use my plot function where for my x argument, I'm just simply going to put x in there. And so how does R treat this then? How does it know what goes on the y and x axis? Someone tell me if I'm only putting an x argument there. Yeah. And so basically what R is going to do is put x on the y-axis and plot it versus an index, which is okay for us because we're observing, let's say, time point 1, 2, 3, all the way up to however many time points we have. And so then I do some stuff to make the plot look nice in terms of x-axis label, y-axis label. I put my grid lines on the plot. Ideally, whenever you do grid lines on a plot, you would want that to be plotted first before any points are plotted on the plot itself. It's best to have the grid lines behind everything. And then to put the actual points on my plot, I use the points function. And this is what we get. And you can see that this looks very similar to what we saw on the Lancaster County website. Okay. So, It's nice to have this plot, but notice what's on my y-axis there. It's just that index. What would be more informative is if we have the date there. What's a key function that we like to be able to use in R to work with dates? Does anyone remember what that function is? As.date. There are other ways to work with dates. That's the one I found to be the best, so that's why I like to work with that. And so what I'm going to do now is when I use my plot function. Now, is this code big enough so that you can see it in the back? Okay. So now for my y-axis, I'm going to specify a y-axis and an x-axis. So y is going to be equal to x. The x-axis is now going to be my date. And so I am going to use as.date to transform what I have in my data frame, which was date. So right now, R just thinks of set1 $date as just characters. It doesn't know it's actually a date yet. And so that's why we need to say, hey, let's treat it as a date. Tell R that indeed it is a date. And so we use as.date with that. And then I say, well, what's the format that the date is in? Well, month is first, day, year. So that's why, and this is just syntax. That's why I use this %m, for example, to mean month. So I do the plot. So now I'm getting some information about date on the x-axis there, and then I add the corresponding points. And here's my plot. Okay. Now, it's still not as informative as I would like. Notice what's on the x-axis. Only year. And so I would like to tell R, hey, I want to be more precise in terms of how I'm labeling what's on the x-axis. So what should I do then to tell R, hey, how about we plot this maybe by quarter or by month, rather than only putting a tick mark for 2022 or a tick mark for 2023? What's the way that I can tell R to give me more information on that x-axis? So I need to somehow tell R to draw the axis, what's on it, differently. What's a function that allows me to work with the axis? The axis function. Perhaps it was a little bit too easy. So, okay. So I'm going to do my plot exactly like I did before, but I'm going to add this little part right here. XAXT stands for x-axis tick mark. And by putting in quotes N there means no, don't do what you would normally do. And so if I do that with the corresponding points as well, this is what I get. Notice I have no tick marks on my x-axis. Now I can then go back and use the axis function to more precisely say what I want there. Basically, what I would like is to have a sequence, you could say, of dates. And how about we go by quarter? So I like to be able to start, let's say, July 1, 2021, go up to January 1, 2024, and how about we do that by 3 months? And so what I can do is generate a sequence of dates using the SEQ function for sequence from my start date to my end date And then I can say, let's do it by 3 months. What's the format that I want everything displayed in? Well, how about we use this format there? If you look at the help, there's a variety of different formats, and I just chose this one here. In this case, I put the year first. So how about I put all this information to something called my.dates. And this is what I get. So indeed, I did get a sequence. I could have used a function called, and I think you see this in the notes as well, seek.date to do this exactly. The seq, if I just specify that instead, it will do it as well. Now, actually, let me restate that. So, what would be a good way to word this as a question? By me specifying seq here, what ends up happening is actually seq.date is run. How would I actually ever know that that actually occurs? How do I know that seq actually says, hey, seq.date, you run instead? How would I know that? This is some now the more finer points of understanding how R operates. Well, as.date is important there. So every object has a particular, in R, every object has a particular attribute associated with it. What's the name of this kind of attribute? What do we often refer to it as? It's like a type, yes, but I'm looking for the formal R name. Class. Yes. Every object in R has a class associated with it. Look what happens if I do this. Suppose I say class, then whatever the results was from as.date. Notice, it's a date class. Okay. Now, in R, if I wanted to see the actual code for a function, what would I do? Let's say if I want to see the code for seq, what would I need to do? Or what could I do? Any function in R, I can do something, I can see the corresponding code to it. This is actually one of the beautiful aspects of R, is nothing's hidden. Help is not going to show me the actual code. Without parentheses. Yeah. Okay. So it says use method. I mean, this doesn't really look to be too uniform, or too uniform, too helpful here. It says use method. What does that mean? So I know all of you, or I should say all of you, many of you taken Stat 850, and I would hope that you would have learned that in that course. What is, for those of you who are stat majors taking Stat 850, use method. What is that doing? Okay. In R, there are what are called generic functions and method functions. Let's do a help now for seq. SEQ is a generic function. Other generic functions in R include, like, for example, the plot function. Maybe another course, like if you've done regression analysis, the predict function. They are called generic because they can behave differently in terms of what the calculations are. They can behave differently depending upon the class of the object. In this case, the class is date. And so since SEQ is a generic function, any generic function, you will see this. Typically, the first line is going to be use method corresponding to, in this case, SEQ. So what R is going to do is first check the class of the data. Then it's going to look, is there a particular function that has been set up to work with that class? What would be the name of this function if I'm working with dates? Yeah. SEQ dot date. Simply, it's the name of the generic function, and you put a dot and then the class name. And there is the actual function that was used with those dates. SEQ.date is called a method function. How would I know what all the method functions that, let's say, are associated with SEQ are? I would say methods class equal, I would say methods generic.function equal SEQ. And we can see, indeed, there was an SEQ.date function there. There happens to be two other ones. So SEQ.default, that's what will be run if there wasn't any kind of associated method function for a class. And in fact, I'll just tell you that if I did this SEQ from equal, let's say 1 to equal 10, by equal 1, that will actually run SEQ.default. Now, if instead I want to do methods class equal date, this will tell me information about what are the corresponding generic functions for objects of class date. And there we are, right there. Notice you will see SEQ. Okay. Well, let's move on. We'll have another example of this coming up. This is a fundamental aspect of using R. And definitely for stat majors, I would really want all of you to understand these fundamental concepts because you'll be able to apply them in so many other situations. Okay, so I created this sequence of dates. I'm going to use the access function, side equal 1, just simply, if you look at the help, means the bottom x-axis. I'm going to, at these particular dates corresponding to what's on my plot, I'm going to put the labels, simply the same dates. If I, for some reason, had different labels from where I am drawing the tick marks at, I could have put that there. It doesn't really make sense in this situation. And so now we have some dates. Now, if you notice that some tick marks don't actually have a date underneath it. And R is using its default way of making sure that things are not, let's say, overlapping. And so if I really wanted to, I could simply make my plot bigger. And now you see all those dates in there. I can also put some grid lines on my plot. Unfortunately, panel.first is not going to work here to use with plot. And so I can use the AB line function to draw vertical grid lines. The AB line function to draw horizontal grid lines. Notice the V there, the H there. And these are actually going to be drawn on top of what was already plotted. So that's not the ideal situation, but that is the easiest one to apply for the situation. If I were to do let's say, if I was writing a paper for a journal, I would be more formal and get the lines underneath. I guess I could show you real quick how you could do that. Let's see here. Notice you see a type argument there. Type equal L for lines. That's what was actually drawn originally. Okay. Instead, I could do type equal N. What that's going to do is, no, don't draw anything and just leave it blank like that. And so then I can put my grid lines on it. I got my grid lines. And then I can do use the lines function, put what's on my y-axis, x-axis, and now I have my lines on there. It's not a big thing like in our class, but in terms of trying to make things look nice, that's something I would do for a publication quality kind of plot. Okay, one last thing with these plots. Actually, let me redraw that plot. Oops, what did I do wrong? There we go. So, we saw that because of how big what was on the x-axis there, some things might not be displayed unless you make the plot wider. And so what you might want to do is, well, maybe I could rotate my dates there so that they don't overlap. And so here's briefly how to do this. Exact same code as what I had previously. So let me go ahead and run that. So there's my plot. Notice, though, I decided not to actually put any labels there. So the way that I did that was I put labels equal false. To actually draw the labels on the plot, I can use the text function. So I say text, relative to my x-axis, I want to draw labels at where my .dates is. Then relative to my y-axis, I want to draw the stuff at negative 225,000. In other words, if you see where my mouse is, I want to actually, notice here's where 0 is. I want to actually draw my labels down here where my mouse is. And so also, I want to RT, rotate them by 45 degrees. Not for sure why the S is there. What are my labels? Well, they're in my .dates. XPD equal true just basically says it's okay to draw outside the normal plotting area where I have my rectangle here. It's okay to draw outside there. I can actually now draw below. And so if I do that, there I have my dates rotated. I have all the dates in there using the same size of my plot. If I want to actually now label put a label for the entire x-axis, I can use mtext for margin text. I want to draw it at side equal 1, meaning the lower x-axis. Line equal 4. Simply R just simply puts, you can imagine, let's say, if you see where my mouse is, here's line 1, then line 2, line 3, line 4. And so if I go ahead and do that at line 4, there I get my x-axis label. I like to go into this kind of a detail because this could be very useful for your own plots. It can be frustrating trying to search the internet, trying to find out, okay, how do I do this? How do I do that? How do I do that? And so what's a very common thing that I've done in the past for time series analysis in terms of plotting, that's what I'm introducing here, so that now you have an example of how to do some of this stuff rather than randomly searching through the web to try to figure out how to do this. Okay. Now let's talk about an ACF plot so we can understand numerically what the dependence is at like lag 1, lag 2, and so on. And so what I'm going to do is open up a new graphics window. And then I'm going to use this option here. So PAR stands for graphics parameters. Does anyone remember from reading the notes what XAXS equal I stands for? What that's going to do? By default, the way that R draws plots is that, let's say you have data between, let's say, 0 and 100 in terms of, let's say, your x-axis values. What R does by default, it actually extends out what's being plotted. I think it's 4% on your left side, 4% on your right side. If you instead put this I option there, it actually draws it at 0 and 100, the minimum maximum value for your x-axis. And so if I use this with my ACF function, notice I have type equal correlation there to do the autocorrelations. Here's my plot. So in the notes I talked about this, that, you know, if I just go back to the default, which is R for regular. Let me actually do a new plot. We get this situation where so when I use the regular method, let's see here. Where did it go? Actually, I might have did something wrong there. So we're running out of time, so I'm not going to go through right now. I have to investigate after class. So we'll skip that. But the main thing is for us to take a look at is this. So at lag 1, so which will be right about here, I have an estimated autocorrelation of about 0.75. And in fact, on the R output in the console window, we can see it's 0.767. So we have some strong positive dependence at lag 1. So that means that, let's say at time, if I just use a t-index time 10, that's really related to time 11. That means at time 20, it's really related to time 21. We have strong positive dependence. Let's relate this now to this plot. Does it look like we have strong positive dependence on that? Yeah, it should. Notice how we're seeing that, hey, I'm up here with this blue dot, and then my next blue dot, I'm still up there. Positive association. If I had negative association, what would I expect to have happen? Well, with this blue dot, where you see my mouse is, I would go way down. And then if I still had negative association, I would go way back up. But we can see that, once we're in a particular place in our plot, we tend to stay there for a while. That means positive dependence. Okay. I did not get through everything that I wanted to here today. That's okay. We can maybe do some of it next time as well. But what I would do is at least post some of this program to my course website, if you want to take a closer look at it. Are there any, well, I guess to end here, are there any questions regarding this example, what we went through so far? So let's take a look at, well, what's next in our class. So 8 p.m., you have a quiz that's due on Canvas. You might remember also on my discussion board, I posted information about how I've changed my office hours to be before our class rather than after our class. If you did not get that message, you should double check your Canvas settings. Now, even though my office hours are going to be before our class, I'm open to answer any questions that you have here after our class too. There just might be a few times where I might have to cut it off after about 10 minutes or so if I have a meeting I have to get to. But I'm open to having questions after class. I will not necessarily be in my office after I leave this room. Now on Thursday, I'll have my office hours at 8:30 in this room here. And then 9:30 we'll have a help class. Again, it's an optional class for you to, it's an optional class. You do not have to come, but this would be a great time to come here to work on your project with your group. Next Tuesday, I'll have my office hours. We'll have class at 9:30. And you need to examine the last subsection of section 2. Let's go talk some more about non-stationarity and a way to handle it, for example. It's also going to introduce some really weird notation. Probably some of the weirdest notation out there in statistics, I think. I know when I first saw it, it's like, wow, that's odd. But this is commonly used in time series analysis. Then we're going to start the first subsection of section 3. Now we're going to look in this subsection more closely at these autoregressive models. This corresponding material in our book is section 2.2 and also section, that would be, section 2.2 of the book, section 3.1 of the book as well. We will continue a little bit of a discussion of project number 1. You will have a quiz that's due that day as well. And then project number 1, of course, is due Thursday, February 15th at 8 p.m. Okay, sorry I took you a little bit extra time. Any last questions? Okay, then that's it for today.